Last time we discussed the metric with spherical symmetry. So we showed that this is the unique solution of the empty space Einstein equations. And so this time we're going to understand the motion of particles in this metric. So the metric represents the exterior metric of any object, like the sun. And this time we're going to understand how particles orbit the sun, either planets or photons, which are bent by the gravitational field of the sun and deflected. The trajectory is deflected. Okay, and when we do this, we're going to see these two very dramatic predictions of general relativity, which were confirmed early in the 20th century. And then there was this long hiatus where it was basically impossible to test the theory until much more recently. Okay, so first of all, I'm going to define RS, just to simplify the algebra. RS to be 2gm, so I don't have to write that out all the time. And we're going to study the action for a massive particle like the Earth is equal to minus m integral square root minus g mu nu x dot nu d lambda. And that action gives the geodesic equation. And it also gives some conservation laws. So let me just be careful and write this out. It's dx mu d lambda, dx nu d lambda. And if you remember, this action is invariant under reparametrizing the world line. So lambda could be any parameter, any choice of parameter along the world line, which is monotonic, just varies in one direction as you go along the world line. So it turns out that in this case of spherical symmetry, there's so much symmetry that we don't actually need to use the geodesic equation. There is so much symmetry we don't need to use the geodesic equation. We can just use the conservation laws. And this is the hallmark of sort of integrable mechanical systems, classical mechanical systems, is that you don't actually need to use the equations of motion. You can just use the conservation laws, and that's enough to completely determine the trajectories. So we're going to use the conservation laws, and we're going to use we're going to study the trajectory in proper time. So let's study the trajectory in proper time, tau, instead of lambda. And if you remember, d tau, by definition, was square root of minus g mu nu dx mu And so it follows from this that g mu nu x dot mu x dot nu is minus 1, where x dot mu is dx mu d tau. Okay, so we're going to use this equation, and that's really just the definition of the parameter tau for a massive particle, one whose world line is time-like. And then we're going to use the conservation laws, which follow from the action, and that will be sufficient to completely fix the trajectory. Now, you might worry, is this all consistent with the geodesic equation? And indeed it is, and I just leave that as an exercise. You can check that the geodesic equation is proportional to d by d tau of g mu nu x dot mu x dot nu, or let's see, the geodesic equation implies that this equals 0. So it's completely consistent with the geodesic equation to set g mu nu x dot nu equal to any constant, and all we're doing is setting it equal to minus 1. Okay, so let's think about these conservation laws. And here we will use Noether. And so P mu. Well, the first thing we need to do is realize what symmetries there are. So if you think about that metric, and you plug that metric into the action, what are the symmetries? Now, little simplification you can use is that, of course, we've got spherical polars. So this is theta, and phi is the azimuthal angle. Theta is the polar angle, and phi is the azimuthal angle on a sphere. And if we have something in an orbit around our mass m, it's convenient to pick the object to lie in the xy plane, right? This is z, x, y. Convenient to place the orbit in the xy plane. And that means that theta equals pi of is convenient to set theta equals pi over 2. That's sort of obvious choice. Let's just choose theta equals pi over 2. Otherwise, we'll have to deal with all these angles. Right? So let's just place the orbit in that plane, and then it's fairly obvious by symmetry that there's nothing going to kick it out of that plane. We'll just remain in that plane. So we can set theta equals pi over 2 and forget about the coordinate theta. It's not moving in theta. Right? So basically, our S will be minus m integral square root minus g mu nu x dot nu, so that's plus 1 minus 2 gm over r dt d lambda squared, and then we'll have plus the r plus 1 over 1 minus 2 gm over r. Actually, let's start calling it rs. 1 minus rs over r, 1 minus rs over r, dr dt, dr d lambda squared. And then since d theta is 0, it's not changing in theta, so we just have to use for the last part of the metric, and sine theta is 1 because theta is pi over 2, so this r squared d phi d lambda squared. Okay, so that's our action. What are the symmetries of that action? How can I get a conservation law? So if you look at an action and if there's some obvious symmetry, which is continuous, there's obviously a conserved quantity. That's what Noether tells you. So tell me a few symmetries. Our dynamical variables are t, r, phi. There are two symmetries of this action, which should be clear. So what are they? Say again?
Translation in t and phi.
And?
Phi.
Exactly. So there's a symmetries. T goes to t plus constant, because obviously this won't change, and t doesn't appear anywhere else. And secondly, phi goes to phi plus constant. Okay? And if you remember from our discussion of Noether's theorem, this is the this conservation law corresponds to energy, and this conservation law corresponds to angular momentum. Okay, so we know that P, let's call it the momentum conjugate to time, which is defined to be the differential of the Lagrangian density with respect to t dot, with respect to dt d lambda, right? And the momentum conjugate to phi, which is the Lagrangian density is, of course, so the action is minus integral d lambda. I've left out the d lambda of the Lagrangian density. And the momentum is the differential of the Lagrangian density with the corresponding velocity. So these are the definitions. These are both conserved. So we're guaranteed that. The equations of motion are going to imply these things are conserved. Now let's work them out. So Pt, of course, is equal to m from here, and then I've got to differentiate this square root. I should have had some minus signs, shouldn't I? There should be a minus sign here and a minus sign there. So Pt is minus m. And then differentiating with respect to the velocity, I get a factor of 2 from the square. I get a half from the square root. So I just get minus m, and then 1 minus rs over r from this factor, dt d lambda, over the square root. And likewise for p phi, this p phi equals, do the same thing here, I get m dr d lambda times over 1 minus rs over r times 1 over the square root. Now, remembering the definition of d tau, you see this square root just converts the d lambda into d tau. So that's equal to minus m 1 minus rs over r times dt d tau. And over here, this is equal to m dr d tau. Why did I call it r? It's phi. M d phi d tau, and I should have had an r squared. It comes from this term. R squared d phi d tau. Okay, so given any action, it's usually easy to read off what the conserved quantities are by seeing the symmetries. And then we can just use them, and we don't have to bother with the geodesic equation. So let's write down the constraint. So g mu nu x dot mu equals minus 1. So that just reads minus 1 minus rs over r t dot squared plus 1 minus rs over r inverse r dot squared, and then we have plus r squared phi dot squared equals minus 1. But now we have these conservation laws, so I can eliminate t dot with this equation and phi dot with this equation, and I'm left with a single equation for r, which we will integrate. So this is equal to, so let me define Pt to be the energy and P phi to be the angular momentum. Let's call it J, actually, not to confuse it with the Lagrangian. And then this equation becomes minus E squared over 1 minus rs over r. So I've just substituted in here dt d tau. In fact, I'm going to get rid of the m. It's just an overall constant. So it's minus e. So e is minus pt over m. This was pt, so minus p over m is just that. Just this factor. And let's define j, p phi over m is j. And so now this first term is just minus e squared over that, over 1 minus rs over r. The second term, we leave it as it is. And this term is j squared over r squared. Okay, so I've now got an first order ordinary differential equation to solve for r of tau. And phi of tau is going to be given by plugging in the solution for r of tau into this equation. So we've got r squared phi dot is equal to j, and we have t dot is equal to e over 1 minus rs over r. Okay, so once I've solved for r of tau, I just plug that solution in here and solve for phi of tau and t of tau. Now this equation is just Newtonian mechanics And the easy way to see that is multiply it by 1 minus rs over r. And let's take this e squared constant to the right-hand side. And then I'm going to, when I multiply by 1 minus rs over r, I'll get the plus rs over r from this term, but I'll pull it over to the left and call it a potential. And so what I get is r dot squared from here. And then I have 3 terms in the potential minus rs over r. Right? That comes from these terms, this term multiplying the minus 1, and I pull the rs over r to the left. That looks like the usual Newtonian potential, because this is 2 gm over r, and this is the kinetic energy for the particle. Then when this term multiplies here, I get j squared over r squared. That's the usual centrifugal potential in Newtonian mechanics. But I get an extra term, which is this rs over r. So I get a 1 over r cubed term minus rs j squared over r cubed equals e squared minus 1. Okay, so these are the, well, all these terms are just the usual Newtonian terms. Right, the gravitational potential minus gm over r, and the angular momentum, the centrifugal force. But this is the new one. And if we compare it, this is down, relative to this term, this is down by rs over r, which is a dimensionless number. And this, of course, is 2gm over rc squared. And for a Newtonian orbit, v squared goes like gm over r for a Newtonian orbit, right? So this goes like v squared over c squared, which is much less than 1. So if the part for circular orbits, let's say, for a circular Newtonian orbit, for a circular Newtonian orbit, we have 2gm over r squared equals v squared over r, or that equation. So I guess there's a factor of 2. But if the planet is moving much less than the speed of light, this is certainly much less than 1. So here is the correction. This is the GR correction to Newton, which is small as long as the planet is moving slower than the speed of light. So let us define V of r to be the effective potential, the effective Newtonian potential, which is all of these terms, to equal minus rs over r plus j squared over r squared minus rs j squared over r cubed. And let's sketch it. So this is V of r, and then we'll immediately see what all the orbits are. Okay, so how did that function go? Well, at small r, the minus 1 over r cubed dominates. It does this. At large r, this term dominates, the minus 1 over rs over r. So it looks like that, right? And at intermediate r, there's a plus 1 over r squared. So as I come in from large r, the plus 1 over r squared is going to take over until this minus 1 over r cubed takes over. And so it will look like that. Okay, now we can immediately see what the orbits are, because the energy of the orbit is this quantity. So this is the energy in this description, and it's a constant. Can be either positive or negative, depending on E. If E is bigger than 1, the energy is positive. If E is less than 1, this energy can go down to -1. So now what are the orbits in this potential? Well, let's consider an orbit which had a very high energy E, and the particle was just coming in from infinity with some E higher than the maximum of this potential. Right? What happens to the particle? Just goes whoop. Energy is constant. All right? Energy is constant. And what this equation is telling you is that the kinetic energy, kinetic plus potential is positive. So basically, if you're above here, it's not possible. The kinetic energy can't go to 0, because the kinetic is the energy minus the potential. If the energy is bigger than the potential, kinetic energy is always positive. So it's impossible for the particle to turn around. It just zooms in and hits 0. What about if I come in a little bit lower energy, a little bit lower E? And by the way, you see the shape of this plus 1 over r squared is proportional to j, the angular momentum. So what's actually going on is the angular momentum is stopping you hitting 0. If we come in on this trajectory, clearly I don't have enough energy to get to r equals 0. I can't get through this barrier, and so I'll just bounce off the barrier and come back out. And that only happens because the angular momentum is large enough. So in 3D space, the reason you're not hitting 0 is because of angular momentum. In this 1D picture, it's because of the centrifugal potential stopping you going to r equals 0. So what about some other interesting orbits? Tell me 2 more interesting orbits. What does a planetary orbital look like in that picture? Yeah, it's the little guy in the bottom of the well. All right, so this would be bound state. It's an orbit which just stays around at finite radius forever. This one would be an unbound orbit. And then we have some interesting other orbits, like we can be down here. I can come out of the singularity at r equals 0 and rebound back into the singularity. Okay, so that's kind of interesting. And we will, this afternoon, I hope we'll understand what those things are. And they're indeed very strange. Okay, you should realize this is very strange because r is really the time inside the black hole. Okay, so let's call this radius r plus, and this radius, the radius where we have a maximum here, r minus. So we have these 2 radii in GR, whereas in Newtonian mechanics there's only 1. Newtonian mechanics, this just continues upwards. So Newtonian mechanics, if j is non-zero, you can never hit r equals 0. Right? That's very intuitive. I have some angular momentum, I'm never going to hit the origin. So this would be in Newtonian, you're up here, Newton. This is entirely due to GR. So let's calculate those 2 radii. There are 2 critical radii. where dV/dr is 0. If dV/dr is 0, that means that I can just sit here. There's no force on the particle because dV/dr is 0, so I can just sit here forever. That means I'm in a circular orbit. Okay, so I can be in a circular orbit here, or I can be in a circular orbit there. In Newtonian gravity, there's only one circular orbit. But in general relativistic gravity, there are two. Tell me what's the difference between this orbit and that orbit? A very fundamental difference. Yeah, this one is stable, meaning that if I perturb it, it's going to stay nearby. This one is not. So if I perturb it, it's either going to fall in or it's going to fall out. Okay, so R plus is the stable. R plus is stable, and R minus is unstable. So if you just write down this equation and solve it, so dV/dr is 0, we get plus R s over R squared minus 2j squared over R cubed minus 3 RSJ squared over R to the 4th equals 0. So that is a quadratic equation for R. And we see R equals there are two roots, R plus and R minus, which are j squared over RS plus or minus square root j squared over RS squared minus 3j squared. And so this is equal to j squared over RS times 1 plus or minus square root 1 minus 3 RS squared over j squared. So RS is a fixed number. So as we decrease j, right? So imagine you've got a particle with some angular momentum, but we're going to decrease j and see how that changes the orbit. Something weird happens when j decreases to 3 to hit the limit. So as we decrease j to the limit square root of 3 RS, this argument of the square root vanishes, and then the square root becomes imaginary, just telling us the solution disappears. And graphically, what happens is that bump disappears. Okay, so we have this bump for finite j, and as we decrease it, we decrease j, this guy's going to fall until eventually the bump goes away altogether. Okay, and so the potential just goes flat at that point. And if you go below any further, there is no and below this point. So this is decreasing j. And so the limit, at the limit, R minus equals R plus equals j squared over R equals j squared over RS, but j squared is 3RS squared. So it is 3RS. This is called the innermost stable circular orbit, or ISCO. Okay, so this is part of the jargon people use in discussing black holes, is that you can't get something in orbit around the black hole. So this, of course, is 6gm over c squared. Can't get anything orbiting the black hole at a radius less than 6. If it's less than 6, then it cannot stay there. It has to spiral inwards, and cross the horizon and hit the singularity. If it's bound, it has to hit the singularity. There's no stable bound orbit. Now, let's study the Perhiliion shift. Okay, so this was the really very dramatic discovery that Einstein made, which convinced him the theory must be right. In fact, Tony Z's book has a nice accounts of all this, and apparently Einstein said about Planck, who was a very great physicist, obviously, he says, I have the hugest respect for Planck, but he obviously doesn't understand my theory because he stayed up all night to learn about Eddington's measurement of the bending of light. And Einstein said if he'd understood my theory, he would have slept through happily. Not worried, because I already knew it was right, even without Eddington's experiment. So, of course, that was a joke. But this is what convinced Einstein he was right, and beyond this point, he really had no doubt that the theory was right. So let's do that. We've got all the maths we need to understand the Perhiliion shift of mercury. And so what we're going to do is solve this equation, r dot squared minus rs over r plus j squared over r squared, the usual Newtonian terms, minus rs j squared over r cubed equals constant. And we also have this equation for phi, that phi dot is j over r squared. So, as Newton had realized, so these are all Newton. These terms are all Newton. As Newton had realized, you can solve these equations exactly without the relativistic correction. You can solve them exactly. And the way you solve them is you consider r, so we consider r of phi instead of r of tau. Okay, so both r and phi are functions of tau, but you know that phi is monotonic in tau, right? Phi is just going to go from 0 to 2 pi to 4 pi to 6 pi to 8 pi. So phi is a monotonic function of tau, so why not consider r as a function of tau, of phi? And the way you do that is trivial. You just say that r prime, which is dr d phi, is r dot over phi dot. Okay, so this is the first trick, and we'll see in a minute why it's so useful. But let's just divide this equation by phi dot squared, so this will give us r prime squared, which is r dot squared over phi dot squared, is equal to r dot squared. Now, phi dot is j over r squared, so j squared over r to the fourth. Okay, so I take my r dot squared equation and multiply by r to the fourth over j squared. So let me just write, let's write that out. So r prime squared is rs over r plus j squared minus j squared over r squared plus rs. Sorry, let's just do these terms. I might as well do the whole thing. R to the, let's do the whole thing. 1 minus rs over r times r to the fourth over j squared equals constant. Sorry, what am I doing? Well, let's put that in here. Okay. So I just pulled the potential over to the right-hand side. But now you notice, and this is Newton's second trick, that we define u to be 1 over r. And so u prime is minus r prime over r squared. Okay, so I can just divide by this r to the fourth factor. And over here I have u prime squared. So u prime squared. And I'm going to set r equals 1 over u and pull this all back on the left-hand side. And I'll get minus rsu. Let me see. Did I? Yes, minus rsu. Now there's a 1 over j squared here. Okay, and then plus u squared. The j squared cancels this j squared. I just get plus 1 over r squared, which is plus u squared. And then minus rsu cubed equals constant. Okay, so that's a nice trick. And remembering, these are Newton terms. This is the relativistic correction. What's this equation for? X dot squared plus x squared is a constant. What does that remind you of? Harmonic oscillator, right? You have a linear term here, but that really doesn't change anything. If I take a harmonic oscillator with a linear term in the potential, it just says that the potential got shifted by a constant. So this is a simple harmonic oscillator. So that's easy to solve. So to convert it into a harmonic oscillator, we just need to eliminate the linear term. So for the SHO, we eliminate the linear term, by a shift of u. U goes to You see, if I shift u, let's say u equals u twiddle plus a, this term is going to generate a term linear in u twiddle, and I can dial the term a to cancel that term. Right? And so if I choose a equals to plus 1/2 rs over j squared, then this cancels the linear term in u twiddle. And that's just saying something obvious. A harmonic oscillator normally oscillates around u equals 0. But if I add a linear potential to a quadratic one, I just get a shifted linear potential. Right? It's just its minimum is somewhere else. And this is the shift. So we can easily write down the solution. The solution is u equals rs over 2j squared, this shift, times 1 plus e cos phi. And this is the simple harmonic motion. With amplitude proportional to e. Proportional to e. Now, u is 1 over r, so we can rewrite that in terms of r. So r is equal to 2j squared over rs times 1 over 1 plus e cos phi. So you probably remember this from first year undergrad as the formula for an ellipse. Where e is less than 1. E is any number less than 1. So that denominator is always finite. This is the ellipticity. And if you sketch the orbits, you know, they just look like this, where phi, I guess phi equals 0 is actually phi equals pi over 2 is the largest distance, and phi equals pi would be the largest distance, and phi equals 0 would be the smallest distance. This is phi. That's r. Okay, so that was all known. This is small correction. And so all Einstein had to do is figure out the correction to the Newtonian orbit, elliptical orbit, which is really a very simple exercise in Newtonian mechanics. So it turns out that with the inclusion of the u cubed term, you can't, it's harder to solve analytically, but you can easily solve it in perturbation theory. So we'll treat the term proportional to rs, the rs cubed term, as a perturbation. And then something very beautiful happens. Okay, so if we work out the equation of motion, the equation of motion for u is, so this is like an energy equation, right? This is the conservation of energy for u. But to get the equation of motion, we just have to differentiate it with respect to u. And so when we differentiate, with respect to phi, when we differentiate it, we're going to get something proportional to u prime in all the terms on the left-hand side, and we'll cancel that, because on the right-hand side we get 0. So we just, d by d phi, just apply that, and we get u double prime is minus u minus rs over 2j squared. That's the shift. It's saying that the motion is just a simple harmonic oscillator, but centered on this point, not on 0. Okay, so that comes from the first two terms. Because when I differentiate this, I get a factor of 2, and this I get a factor of 2. But here I get no factor of 2. So I divide by the 2, and I'll get that term. And then, of course, I've got my u cubed term. So this is plus 3 over 2 rs u squared. Okay, so all of this is my shifted simple harmonic oscillator with the solution 1 plus e cos 2 phi times this constant. And here is my perturbation. This is my GR perturbation. So how do we solve this equation? We solve in perturbation theory. We say u equals u of 0, which solves this, plus delta u. And the delta u is much less than u0 with delta u small. So if I substitute this formula into here, obviously the u0 terms will cancel. I'll just get terms involving delta u. So I get delta u double prime equals minus delta u from these terms. But over here, I simply substitute in the u0 because my rs is the small parameter. Okay, so I get, so to first order in that small parameter, this is what the equation looks like. 3 halves rs u0 squared, u0 squared, and u0 we know. So this is equal to minus delta u with a driving term, which is 3 over 2 rs. And then u0, I've got u0 over there, so it's rs over 2j squared squared times 1 plus e cos phi squared. Okay, so what is this? Well, this is a driven simple harmonic oscillator. This is a driven SHO. So this guy is the driving force. Right, so remember that phi is the time in this simple harmonic oscillator. This force is a function of time. Now, without going any further, if you thought about this equation, you should be able to say something dramatic is going to happen. So what happens when I drive a simple harmonic oscillator with some force? It's a periodic force, right? This force is periodic in phi. I got my oscillator, like a pendulum, and I'm driving it with a force. Now, this of course, has 3 terms. There's 1 plus, this is a constant force, Constant force is not going to do much. It'll just shift the center of the oscillations, right? So this constant won't add up over time, won't create an effect which adds up over time. This, and then I have plus E squared cos phi squared. Now, which term is important? Cos phi squared, of course, is a linear combination of cos 2 phi and a constant. Cos phi squared is, what, plus 1? Sorry, minus 1 over 2? No, plus 1 over 2. Okay, so these terms give me constant and frequency 2. If I drive a simple harmonic oscillator with frequency 1, with a force with frequency 2, do I get anything dramatic happening? What happens if I hang a pendulum, which has a certain frequency, and I drive it with a force of the same frequency? What happens? Resonance. This one is the resonant term, right? You're driving the oscillator at its resonant frequency. So this is resonant frequency. Okay, I'm not sure if Einstein realized that, but that should be obvious with hindsight. This term is going to give all the interesting effects because you're driving this periodic motion with a force of exactly the same period, and that builds up resonance. This one's completely uninteresting because you're driving the oscillator with twice the frequency. It doesn't build up at all. It just introduces a little wiggle of twice the frequency, but doesn't grow. Okay, so let's forget about these terms. We'll forget the constant. You can solve it, it's not difficult. Forget the constant and cos 2 phi terms because they're not uninteresting. The resonant guy is interesting. And so this looks like delta U double prime is minus delta U plus. And let's work all this out. We get 3/4 RS cubed over J to the 4th E cos phi. Okay, factor of 1/8 from these factors, factor of 2 from there, and an E. So notice that the ellipticity of the orbit in Newtonian theory governs the strength of the effect. If the ellipticity is 0, as it is for a circular orbit, there is no effect. So we want to solve that equation. Well, if you're lazy, you can just put it into Mathematica, right? And it'll give you the solution. But what you're really looking for is a growing amplitude oscillating solution. And let us write it down. So the solution is delta U of the growing solution. Delta U is 3RS cubed over 8 J to the 4th E phi, sine phi. I've changed from, yeah, sorry, my phi is not particularly consistent, but it is always the same phi. Let's check that. So if I differentiate this thing twice, delta U double prime, obviously if I differentiate this term twice, I get nothing because it's linear in phi. If I differentiate each term once, I get a factor of 2 times so let's just say, let's take the phi sine phi. Only forget the constant. Differentiate this twice, I get 2 times phi prime, which is 1, times sine phi prime, which is cos phi. So this gives me 2 cos phi. And if I differentiate it, differentiate the sine phi twice, I get minus phi sine phi. Okay, so when I calculate the delta u double prime, I'm going to get minus phi sine phi, which is exactly the right term to equal this one. And then I'm going to get a constant times cos phi, which will be exactly that term. Okay, so this is the growing perturbation created by the resonant driving force. So phi, as I said, phi goes from 0 to 2 pi to 4 pi to 6 pi to 8 pi. That amplitude keeps building up, right? And so this is the interesting term. So we get u, the full solution, is approximately u0, which is rs over 2j squared times 1 plus cos phi, plus e cos phi. And then we have this correction, 3 rs cubed over 8j to the 4th e phi sine phi. Which is growing. Now, this is a small coefficient. And so we can rewrite this as follows, approximately rs over 2j squared times 1 plus e. What we notice is that sine phi is the derivative of cos phi. So if what I do is shift the coefficient of the phase, if I shift the coefficient of phi inside the cosine, I will actually generate this term. So let me write it down. Cosine 1 minus epsilon phi, where epsilon is a constant, where epsilon is chosen just to, epsilon is a small number chosen just to reproduce that coefficient. Epsilon equals 3 rs squared over 4j squared. Okay, so this is correct up to order epsilon plus order epsilon squared. So epsilon is the dimensionless number chosen to generate this term. This is called a secularly growing term. That just means that as the particle orbits and orbits and orbits, this term gets bigger and bigger. But what this trick amounts to is saying that is actually a resummation of perturbation. The perturbation series, you can regard this as a perturbation. This is a perturbation. It's growing. In this form, perturbation theory fails, because at some point, this phi sine phi is going to get bigger than this term. Right? So perturbation theory fails in this form. Fails. If I write it this way, it never fails. Right? Because this represents a resummation of perturbation theory. to prevent the breakdown, to prevent its breakdown. Okay, so in this form, both of them are valid. This one only valid for small phi, this one valid for arbitrary long phi. So obviously this one is much better. And it's really just telling you what that perturbation does. It shifts the oscillation frequency. So whereas this particle, the Newtonian particle had a certain frequency, the relativistic particle has its frequency shifted. And that means the orbit is not periodic in phi. And that is the perihelion shift. Okay, so this tells us that R is 2j squared over Rs over 1, approximately to order epsilon, 1 plus E cosine phi, cosine of 1 minus epsilon times phi. So it means it is not periodic in phi. Instead, it is periodic in 1 minus epsilon times phi. Okay, so whereas the original orbit was repeated itself as phi changed, as phi went from 0 to 2 pi, the original orbit repeated. This one doesn't quite repeat. You see, as phi comes back to 2 pi, this argument is not 2 pi. It's a little bit less than 2 pi. So you're going to have to wait a bit longer in phi. Phi will have to equal 2 pi over 1 minus epsilon in order for the orbit to come back, meaning that the radius takes the same value. So the orbit doesn't quite come back. So instead what happens, you have to wait a little bit longer in phi to reach the maximum radius. And so the orbit shifts around like this. Okay. And so this shift, so delta phi, the extra phi you have to wait in order to reach the maximum radius, is defined as follows, that 1 minus epsilon times phi plus delta phi should equal to 2 pi. Sorry, 2 pi plus delta phi. To order epsilon, i.e., delta phi is equal to epsilon times 2 pi. And so basically what I get here is the argument of the function will be 1 minus epsilon. And then I'll have 1 plus epsilon times 2 pi. And this is 1 to order epsilon squared. So phi has to wait a little bit longer, and delta phi is this epsilon over 2, is 2 pi epsilon. So we get the perihelion shift. Coming about from this resonant behavior. So the change in well, it's called the Perhiliion shift. That's just the change in the angle required to reach maximum radius. To reach the same radius. Let's say reach the maximum radius. Delta phi is equal to 2 pi epsilon. So it is 2 pi times 3 rs squared over 4j squared. And so these numbers are known for the planets. Rs is just 2gm, so that's the mass of the sun. Rs is 2gm sun over c squared. And J is the angular momentum for the orbit of Mercury. J equals the angular momentum, or it's determined by the angular momentum. And so it turns out that for Mercury, which is the planet nearest the sun and therefore most strongly affected by this effect, for Mercury, delta phi is 5 times 10 to the minus 7 radians per orbit. So it's really small. It's less than a millionth of a radian per orbit. Mercury has 415 orbits per century. And so this leads to delta phi equals 43 arc seconds per century. In precise agreement with the astronomical anomaly. Okay, so this was known in the 19th century that Newtonian mechanics didn't quite work for Mercury. It wasn't known why. This is a very tiny correction. I mean, this result was centuries of astronomical work went into getting this result. The correction due to Jupiter. So Jupiter is a big planet, and it influences the orbit of Mercury. And Jupiter is a correction of 200, or more than 200 arc seconds per century. So they had already taken out that correction, made various other corrections, and this was the residual that they couldn't explain using Newton's laws. Even after this explanation, many people doubted it. You may have heard of Bob Dicke. He was a professor at Princeton, and one of the people who really led he led the Renaissance in general relativity experiment in the 60s. And so Dicke, for a long time, argued that maybe this was just due to the quadrupole moment of the sun. The sun is not perfectly spherical, all right, and that introduces a correction. Obviously, the monopole of the sun gives a 1 over r term, but the quadrupole gives a 1 over r cubed. And he argued maybe that 1 over r cubed was enough to create this effect. And it was only when people measured the sun precisely enough, they could rule out that the quadrupole moment of the sun being the explanation for this effect. So that some people still doubted it into the 1960s. But the quadrupole moment turned out to be irrelevant, and this effect has by now been very strongly confirmed in other experiments, for example, by sending satellites near the sun and see what the effect of a satellite on the orbit of a satellite. Just follow this satellite orbit carefully and calculate this perihelion shift. So by now it's well verified. Okay, so any questions? If not, I'm going to, yeah.
So when we measure this, the perihelion shift, how do we get the J?
How do we get this?
Yeah.
Okay, we'll have to trace back where it came from. I don't know if the equations are still there. Basically, it's coming from this equation, right? So phi dot is J over R squared. That was the definition of J. It's whatever constant appears in here. And so we're allowed to use, so in other words, J is phi dot R squared, is a constant. And so what we do, let's draw our orbit. Okay, so of course the velocity of the particle, v, is r phi dot. Okay, and so j is just rv. So j is rv. So to measure j, we have to measure the distance of the planet at its maximum, and we have to measure its velocity. And then j is just rv. That's the angular momentum per unit mass.
Why is it possible to use Schwarzschill metric?
Sorry?
Why is it suitable to use Schwarzschill metric to analyze?
Oh, because if the sun is spherical, then our derivation of Schwarzschild metric is absolutely correct. Because outside the sun, we have a solution of r mu nu equals 0, right? T mu nu is 0 outside the sun. Inside the sun, T mu nu is not 0. But outside, r mu nu equals 0. And if the sun is spherically symmetric, then the metric outside must be spherically symmetric. Okay, so kind of nice. You see, it doesn't. By the way, imagine the sun was really a bouncy ball, and the sun was bouncing radially, right? It actually wouldn't change anything. The metric outside would be absolutely static, because we proved it's static. The spherical symmetry ensures the only allowed metric is static. It doesn't matter what the source is doing. In fact, if the sun, imagine the sun exploded, and it came outwards at the speed of light. All the matter came out at the speed of light. We would be sitting here, and we see nothing until the shell reached us. There would be no warning. Right? The metric would not change outside the sun at all. So because of Birkhoff's theorem is very, very powerful. It says as long as you have spherical symmetry, the metric outside some kind of stress energy is strictly Schwarzschild. There's nothing else it can be. Okay. All right, so I think I want to discuss one last thing, which is the bending of light. Well, I'll tell you what. Since we're meeting this afternoon, I'll give you a choice. We can do the bending of light. It's a fairly standard derivation. It's pretty much like this. It gives a similarly dramatic result, that the bending angle of the light is fixed. I can skip it, and you can have a break, and we can meet this afternoon and fall inside a black hole. or I can do it. I don't mind. Maybe I should skip it. It's in the textbooks. I'm not going to really give much of an improved derivation. So I think probably better for you to have a break. And then we'll meet this afternoon at 2. And this is really very different, because when we discuss this afternoon what happens when I fall through the Schwarzchill radius. And that is very, very mind-bending. And we'll see all of this, but from a completely non-Newtonian angle. There's absolutely no connection with Newtonian physics at all. Okay, so I would just skip bending of light. Are there any other questions? See, bending of light is really, we just point out one thing. When you do the bending of light, much of the derivation we did is actually the same. What's the difference? When did I assume I had a massive particle as opposed to a massless particle? Is it somewhere up there? Probably erased by now. Yeah, I did erase it. Remember, I basically defined tau, right, this way. That defined the tau. What would I do for a massless particle? 0. Now, just be a little bit careful about this, because there is no tau for a massless particle. d tau is dt squared minus dx squared. It's 0 for a massless particle. So this is no longer tau. For a massless particle, this is not tau. Okay, instead, what is it? So what is the dot? Well, you really have to just keep this equation with lambda. So lambda is a parameter along the world line, and you're free to change that parameter however you like. Okay, but we want to use this equation, and in fact we need to worry a little bit about the action, because the action was the square root of something which is 0. Okay, so the action is 0 if you're not careful for a massless particle. So you really don't want to put this into the action, otherwise your action is 0. So it's somewhat delicate, that's all I'll say. But it turns out photons do obey the geodesic equation, this d lambda squared plus gamma mu nu lambda dx nu d lambda dx. So photons obey these two equations. They are consistent. Lambda here is, the lambda is called an affine parameter. Okay, an affine means that you can change it by an overall constant and you can shift it. So an affine transformation is lambda prime is a lambda plus b with a and b constants. You can see if I do any of those transformations, it leaves this invariant and it leaves this invariant, because the powers of d lambda are the same. Okay, so for photons, these are the equations you have to use. There is a better action than the square root action, which I haven't described. The better action is sometimes called the Perhiliion action, or whatever, whoever it's I think wrongly attributed, but there is a better action which you can use for photons. I won't have time to describe it, but these are the right equations for photons. And so let's just track what happened to the 1, and what did the 1 lead to in this formula. If you work it through, you will discover, whoops, that the only change here is that for photons there's no term there. There's no Newtonian potential for photons, right? So photons just obey this equation. Now, given that, you can see the 0th order solution for a photon is these two guys. And so that is simply the motion of a particle in the absence of any force. That's just the centrifugal force. So the zeroth order solution for photon is a straight line, right? R, and this is phi, and it just goes through as a straight line. If I drop this term, photon just goes through as a straight line. And this says that R is proportional to, R sine phi equals constant. That's a straight line, right? Because this is R sine phi, and that's constant. So the zeroth order solution is that R is proportional to sine phi when I do all these tricks. Okay, so the zeroth order is this, and then I have some source for the U, and you go through all the same algebra, and you find that the photon path is bent like that, and the bending angle is some particular value, and this is what Eddington went to measure. In fact, that's also a funny story, which is recounted in Z, is that Einstein first predicted the bending of light, and he got a factor of 2 wrong. Actually, Z doesn't explain it correctly. If you go back and read Einstein's paper, his first paper, it's clear why he got it wrong. It's because he used G00 only. See, what he already knew at that point is that G00 recovers Newtonian theory. If G00 is 1 minus 2 phi, then you recover Newtonian theory for massive particles. So when he did the bending of light for the photon, he just took G00 and he ignored Gij. Because he didn't know what it was. They just ignored it. And that's why he got a factor of 2 wrong. Because in the Schwarzchill metric, the perturbation to G00 and the spatial perturbation, the dr squared over 1 minus, they're actually the same perturbation, apart from being inverted. And that gives a factor of 2. So during that time when Einstein had predicted the bending of light, a lot of people mounted experiments to check. And so there was a German group, and there were various other people doing it in Europe, and all of those experiments failed. It was too cloudy, or there was a war, or there were all kinds of reasons, right? Why none of those experiments, I think there were at least 2 and maybe 3 experiments which Z describes, and they all failed. And then during that time, Einstein realized, oops, so he got his field equations, he got the spatial components of the metric, and then suddenly he realized, whoops, I made the wrong prediction for bending of light. And he corrected it by a factor of 2. And then shortly afterwards, Eddington mounted his expedition and did measure it, and it agreed perfectly. So Einstein had luck like you cannot believe. Because, imagine if people did the experiment, they said, oh, no, he's wrong by a factor of 2. That would be very embarrassing for the theory. And people would have said, oh, this theory is no good. But it never happened that way. So, yeah, amazing history. Right, so I will see you this afternoon at 2.